Yeah, so I'm grateful for the chance to tell you about some of my group's work today. I'm going to tell you about my favorite superconductor, strontium ruthenate, and this talk concerns a single question: is strontium ruthenate a chiral superconductor? As I go along, I'll tell you, I'll introduce some of the people who've contributed to this work. Just first, I want to start with the general slide on why we are interested in chiral superconductivity. In most of this conference, the theme has been trying to trying to create topological superconductivity and then finding ways to use that. I want to look a bit in the other direction. What does it mean when we have a chiral superconductor in terms of the mechanisms of superconductivity? So I'll draw here a hypothetical, very simple cylindrical Fermi surface with a chiral order parameter, so homogeneous gap magnitude, and then a phase that winds from 0 to pi over 2 to pi as we go around the Fermi surface. I also draw a hypothetical electron-electron scattering event from the filled orange circles to the open dashed circles. So across this scattering event, the phase changes by...
Sorry for interrupting, but I'm not sure whether have you changed the slide already?
Yes.
We haven't seen that. We are still stuck in the SRO.
Oh, right.
Now we can see it.
Now you can see it. Okay, I'll just stick with this move.
Sorry for that. Well, so you come back to the people, so we want to see the pictures of the people who were involved on names. Sorry for this. Yeah, okay. Is this the very first one then?
This is the that was my title slide, and this is my first slide.
No, brilliant, awesome. Thank you so much. Sorry for that.
Okay, good. I'll stick with this then. So, right. So as I was explaining, we have a cylindrical Fermi surface, and then a hypothetical gap where the phase winds from 0 to 2 pi as we go around the Fermi surface. And then I've drawn on here a hypothetical electron-electron scattering event from the filled orange circles to the open dashed circles, in which the phase changes by pi over 2. And the point is that when scattering events where the phase changes by pi over 2 do not contribute to the condensation energy, whether the pairing interaction is attractive or repulsive, this scattering event does not contribute to the condensation energy. In BCS theory, however, TC is exponentially sensitive to the number of charge carriers that participate. So whenever you have chiral superconductivity, you have to ask the question of how we're able to get superconductivity at all in spite of this strong frustration of the pairing interaction. In strontium ruthenate, as I'm going to now tell you, the question is even more heightened because in the light of recent data, if the superconductivity is chiral, we really have no idea in a conventional picture of why, of where the superconductivity could come from. So it could be telling us that we need a new pairing mechanism. So a quick introduction to strontium ruthenate. It is a Fermi liquid with modest mass enhancement. It has 3 Fermi surfaces, alpha, beta, and gamma. So the mass enhancement is about 3 for the alpha and the beta sheets, and then the enhancement over the bare band value is about 5.5 for the gamma sheet. So the gamma sheet is the most strongly correlated. The resistivity is Fermi liquid-like below about 30 Kelvin. This curve here is the in-plane resistivity, and here is the c-axis resistivity. The c-axis resistivity is measured in units of milliohm centimeters, and the in-plane resistivity microohm centimeters. So the electronic anisotropy is about a factor of 1,000. There is strong Hund rule coupling that suppresses orbital fluctuations. So these Fermi surfaces here are ARPES data from the Baumberger group at the University of Geneva. And then here, the Fermi surfaces are colored by their orbital content. The gamma sheet is mostly XY, but with mixing of XZ and YZ orbitals at the corner. And likewise, the beta sheet is mostly XZ and YZ, but with mixing of XY at the corner. When the self-energy is resolved by orbital character, it is found to fall on 2 distinct lines. This blue line for the XZ and the YZ orbitals, and this red line for the XY orbital. The different shadings within these lines correspond to different points on the Fermi surface. So the point of this graph is that wherever you are on the Fermi surface, the self-energy is determined by the orbital content. So in other words, electronic correlations appear to be very strongly a property of the orbital and not the Fermi surface and the position in K-space. So now onto the superconductivity of strontium ruthenate. It is without doubt unconventional. TC is very strongly suppressed by residual impurities. If the mean free path is less than about 100 nanometers, then TC falls to 0. This extreme sensitivity to impurities is characteristic of unconventional superconductors. What makes it more unusual is the indications of chirality. So this panel on the right is the Kerr rotation versus temperature, the angle by which the polarization of light rotates when it is reflected from the sample. So there's a non-zero Kerr rotation that onsets at Tc. So this indicates that the superconductivity has a rotational sense, in other words, that it is chiral. More evidence for chirality comes from experiments from the Maino lab at Kyoto University. So here is a junction between niobium and strontium ruthenate through a ruthenium inclusion. So in this photograph at the top, the brown areas are all covered with silicon oxide, and then the blue areas is where the niobium thin film contacts the strontium ruthenate. The strontium ruthenate itself has an insulating surface layer. So to get a superconducting junction, it's necessary to go through a ruthenium inclusion. The critical current then of these junctions shows some very unusual behavior. So at 0.5 Kelvin, there's this switching behavior. So the x-axis is applied current, the y-axis is voltage. So the critical current is somewhere in here, but rather than seeing a single critical current, what they observe is this strong fluctuating behavior. And that is an indication that there are domain walls within the superconducting state that can move. Another indication of domain walls from a junction experiment comes from the Van Harlingen group in Illinois. This is their setup. They have a sample of strontium ruthenate with lead thin films bonded to the side, and then they measure the critical current through this junction as a function of applied field. And in some cases, they saw a classic Fraunhofer pattern with a maximum critical current when there's no applied field. But in many junctions, they saw this very unusual behavior shown in panels B, C, and D. These are just 3 different examples. They see a critical current that is small and essentially fluctuates randomly with applied field. And what they concluded from this, again, is that there are domains within the superconducting state that give the that results in a complicated phase structure within the junction. So that's the evidence. That's some of the evidence for chirality. Now, one thing that has changed recently in strontium ruthenate is that NMR night shift evidence now supports even parity pairing. So on the left-hand side, I show data from Stuart Brown's group at UCLA. This is the NMR intensity versus pulse energy at a temperature of 20 millikelvin. With the highest pulse energy, the electrons are kicked into the normal state, so we don't see the superconductivity. As they reduce the pulse energy, you can see the oxygen resonance positions shift. So this is the X oxygen, this is the Y oxygen within the ruthenium oxide planes. So this shift indicates a decreasing spin susceptibility within the superconducting state and opposite spin pairing. Then Kenji Ishida from Kyoto University measured this as a function of temperature. Here's the night shift, and the night shift decreases below Tc. So the spin susceptibility decreases below Tc. Further evidence for even parity superconductivity comes from uniaxial stress experiments. So here I show an ARPES measurement of the Fermi surfaces of strontium ruthenate under an in-plane compression along the x direction by about 0.5%. And what one sees is that the Fermi surface goes through a Lifshitz transition right at this point. The gamma sheet transitions from an closed to an open geometry. As it does so, Tc passes through a very pronounced peak. Tc more than doubles to about 3.5 Kelvin. Here it seems a little bit higher. The upper critical field at this peak is very strongly enhanced. So in this graph at the top, here is Hc2 versus temperature at the Lifshitz transition, in other words, at this point here, and then this is the curve for unstrained strontium ruthenate. So the zero temperature enhancement from here to here is a factor of more than 20. The more pertinent quantity is Hc2 divided by Tc squared. If all we did was somehow scale the gap magnitude, this quantity should remain constant. Instead, in the zero temperature limit, it increases by a factor of about 3.5. And what that tells us is that a large gap coincides with a small Fermi velocity more than an unstressed strontium ruthenate. That's very suggestive because the place where the Fermi velocity is smallest is right around here, right at the zone boundary. By symmetry, right at that point itself, the Fermi velocity must fall to 0. So if we say that we have, now the thing is that this point here is the same as that point here. It is a single point in K-space. It is a parity invariant point. So if we say that we have a large gap magnitude here, it must be an even parity gap. So now the challenge is we've got to reconcile evidence for even parity pairing with chirality. So the lattice of strontium ruthenate is tetragonal. The only order parameter, the only chiral order parameter where both components are degenerate on a tetragonal lattice is dxz plus or minus I dyz. So at L equals 1, even parity order parameter. What's problematic with this order parameter is it has this line node at kz equals 0, the symmetry imposed line node. And that means that the pairing in conventional understanding would be dominated by interlayer interactions. And this is really unexpected because the interlayer interaction is weak. As I told you earlier, the ratio of the resistivities is about a factor of 1,000. So this is why the question of whether strontium ruthenate is chiral or not is really important. If we confirm that this is the order parameter of strontium ruthenate, then we are forced to start looking for new pairing mechanisms to explain how this can occur in such a two-dimensional material. So my group has been working on uniaxial stress experiments to probe this question further. So under in-plane uniaxial stress, the tetragonal symmetry of the lattice is lifted and the degeneracy of x and y components of the superconductivity is lifted. So we expect a phase diagram as shown here. As we apply uniaxial stress, we have two transitions, a higher transition into the superconducting state, and then a lower transition into a chiral state. So within this space, we might have dxz superconductivity alone, and then down here, xz plus iyz. The characteristic form that we started looking for first was this cusp that this phase diagram predicts in Tc, this cusp right at 0 stress. And here are results of the experiment. So here's the setup on the right. This black bar is the sample, and this is mounted between jaws through which we can apply force, compressive or tensile, along the length of the bar. And then we have two coils placed on top. Here's the smaller one, here's the larger one, through which we can measure Tc. So here's Tc versus strain for two samples. And in both cases, we see that whether we compress the sample or tension the sample, Tc indeed increases. So as soon as we lift the tetragonal symmetry of the lattice, Tc increases. However, the form of the dependence on strain is U-shaped rather than this cuff-like form that we hypothesized for chiral superconductivity. So my colleagues at Oxford, Steve Simon and Thomas Cafidi, performed weak coupling calculations of the expected cusp magnitude for pH plus minus IPY superconductivity, and this is what they obtained. So this is the predicted cusp for a weak coupling calculation on top of our data. And you can see that with a reasonable amount of impurity broadening, actually even quite a low amount of impurity broadening, we could round out such a feature. So this data, while it's exciting to see that we can raise Tc, does not provide conclusive evidence on whether or not strontium ruthenate is chiral. To improve resolution, my colleagues at Stanford, Cam Moeller and Chris Watson, performed scanning SQUID microscopy on strontium ruthenate. So here's the essential configuration of the setup. There is an excitation coil around a pickup coil. This pickup coil is coupled into a SQUID. The measurement is of the mutual inductance between these two coils. When we bring the sensor close to a superconducting material, the Meissner screening of that material screens these coils from each other, and that mutual inductance decreases. So here's some data on strontium ruthenate. This here is the edge of the sample. The temperature is 1.43 Kelvin, so we're just below the bulk TC, and the color scale is the coil mutual inductance. Blue is strong superconductivity, bright yellow is no superconductivity at all. And what they see is these streaks, where TC is a little bit higher than elsewhere. Such inhomogeneity always occurs in real samples. Within this particular sample, the spread of TC across the sample is about 50 millikelvin. But what they can do with the scanning SQUID is they can park the scanning SQUID in locations away from these streaks where the superconductivity looks homogeneous, and they can measure TC right there. And this is what typical data look like. So this is the mutual inductance between those coils versus temperature. Here is TC. They have millikelvin resolution on TC. So now they measure TC versus applied strain. The different colors here correspond to the different color points in this large area scan. And at each point, they see a quadratic dependence of TC on strain. So once again, they did not see a cusp in TC versus strain. Another experiment performed in Dresden is AC heat capacity. So the essential experiment is here. Here's our bar of, here's the essential setup. Here's our bar of strontium ruthenate. There's a heater attached to the middle of the sample, and then also a thermocouple. And by applying the heat at a very high frequency, the temperature oscillations are confined only to the center of the sample. So here now is data versus temperature. So here I plot 1 over the thermocouple oscillation amplitude. This is qualitatively related to the heat capacity. At 0 strain, we can clearly see the jump in heat capacity at the superconducting transition. And as the sample is compressed, we can see this TC move on up as the Van Hoff singularity is approached. The key result here is that at no strain can we resolve a second transition corresponding to that into a chiral state. So for example, here at 0.3% compression, here is TC, and we do not see a second jump corresponding to the second transition. So the limit here is that if there is a chiral transition, the heat capacity jump at that transition is at most about 5% that at the superconducting transition. So if strontium ruthenate is chiral, this chirality is thermodynamically very delicate. So in thermodynamic probes, we have not had much success in finding evidence for chirality in uniaxial stress experiments. So now in collaboration with the group of Hans Henning Klaus at TU Dresden, we performed muon spin rotation experiments on strontium ruthenate. This has been part of a multi-year effort. Now we've got some conclusive data to share with you. These experiments were done at the Paul Scher Institute in Switzerland. So in this technique, spin polarized muons are implanted into the sample, and then each muon precesses in the local field. So if there are random internal fields within the sample, the muon polarization steadily relaxes. By collecting statistics on the positron emission direction as the muons decay, the muon polarization can be tracked as a function of time. So this is what typical data look like. This is from the first measurement of strontium ruthenate by muon spin rotation, published in 1998. Here's the positron emission asymmetry, in other words, the muon polarization as a function of time. Here at 2.1 Kelvin, what they saw was a steady decrease in the muon polarization. So that's due to internal nuclear magnetic fields. Going to lower temperatures, this relaxation rate increases. And if you plot the relaxation rate versus temperature, that increase is seen to onset at TC. So there appear to be random internal magnetic fields associated with the superconductivity. At the time, the microscopic mechanism for this was thought to be edge and domain wall currents. So if you have a chiral superconductor, you can, as a cartoon, you can draw the Cooper pairs as little current loops, and these pile up at the edge to give you a net current along the edge. That edge current will generate a magnetic field. It is screened by the Meister screening current, but along the edge, there is some field that escapes from the sample, and similarly at domain walls. John Kirtley and I looked for these edge fields through scanning SQUID microscopy. So this is now a magnetic field as a function of position, and then right here at 0 is where the SQUID crosses the sample edge. These dashed lines are a prediction of the expected edge fields under hypothesis of chiral superconductivity, and this solid black line is what was actually seen. So in other words, so in other words, the upper limit on the edge field from scanning SQUID microscopy is 2 to 3 orders of magnitude less than the prediction for chiral superconductivity, and way smaller and much smaller than the fields seen in Muon spin rotation. Nevertheless, although the microscopic mechanism is not known, there is strong empirical evidence that enhanced Muon spin relaxation really is tied to time reversal symmetry breaking superconductivity. So here's data on uranium platinum-3. Here's the Muon spin relaxation rate versus temperature, and this is seen to increase below a temperature T prime of about 0.48 Kelvin. This material is superconducting. TC is 0.55 Kelvin, but then at 0.48 Kelvin, it transitions into a chiral state. That is also shown with Kerr rotation versus temperature. Here is the onset of chirality. And in UPT3, in uranium platinum-3, the evidence is clearer. Chirality has also been seen in small angle neutron scattering experiments and junction experiments. So it's unambiguous. It's a lot more certain than strontium ruthenate. Okay, so now some of our data on strontium ruthenate. So here are data from 3 separate samples. The solid black lines are the heat capacity, so the TC is readily visible, and the Muon spin relaxation enhancement for samples A and B start right near TC. For sample C, the time reversal symmetry breaking temperature seems to be a little bit lower. In no sample that we've looked at have we seen the time reversal symmetry breaking temperature exceeding TC. The main point I want to emphasize here is that it really looks like a transition. So the Muon spin relaxation is flat until we hit TC, or maybe a slightly lower temperature, and then it increases. So there may be some rounding here due to sample inhomogeneity, but there's no large-scale rounding. So now we want to repeat this experiment under uniaxial stress. So we built this uniaxial pressure cell. It's about 20 centimeters long. It uses piezoelectric actuators here to compress a sample which is placed here. Here's a photograph of a sample. This black square here is a plate of strontium ruthenate. We placed behind this sample susceptibility coils to measure TC in situ. Okay, and here are some data now under uniaxial stress. So these data are all from the same sample. This is at 0 GPa, about 0.3 GPa compression, and about 0.4 GPa compression. And we see TC steadily increasing as expected, but the time reversal symmetry breaking temperature remains low. At 0 GPa, it's perhaps 0.1 or 0.2 Kelvin below TC. Now at 0.3 Kelvin, it is definitely lower. The time reversal symmetry breaking temperature decreased in this sample from about 1.4 to about 1.2 Kelvin as the stress was applied, and then it appears to have saturated at that temperature as the stress was increased further. Going to higher stresses, going to higher stresses, my colleagues at TU also observed spin density wave order. So now we're under a stress of 1.0 GPa. This is beyond the Lifshitz transition, and at 7 Kelvin they see a normal spin normal spin relaxation at lower temperatures, they see these oscillations in the polarization. That is a typical response for spin density wave order. And then here, this is the internal magnetic field extracted from these plots on the left versus temperature. The nil temperature is about 7 Kelvin. So the estimated zero temperature ordered moment is about 0.06 Bohr magnetons per ruthenium. Now this tells us something. So this form, when we have magnetic order in strontium ruthenate, is completely different from the muon spin relaxation seen at lower stresses. So this is a strong argument that this enhanced relaxation here is really not from magnetic order. If it were from magnetic order, the ordered moment would have to be only about 2 millibohr magnetons per ruthenium. So that is an extremely low ordered moment that simply does not occur in real materials. Another hypothesis could be that it is localized spin density wave order. However, in this case, the islands of spin density wave order would grow as we applied stress and we approached the bulk spin density wave order, and that is not seen. Another potential hypothesis is ferromagnetic fluctuations. However, ferromagnetic fluctuations fade very slowly as you raise the temperature, whereas, as I showed you before, what we really see is this transition-like onset. So here's the phase diagram of strontium ruthenate from muon spin rotation. From the absence of plausible magnetic mechanisms to explain the enhanced muon spin relaxation, we conclude that it really is a transition of the superconductivity, and then we have this transition from superconductivity, from normal, well, time reversal symmetric to time reversal symmetry breaking superconductivity at a temperature of about 1 Kelvin. And then at very high stresses, we have the spin density wave order here. So another experiment that has also recently given evidence for chirality is ultrasound resonance. So when you have a continuous transition, the free energy decreases quadratically as you go below this transition. So now, if this transition has a finite slope with applied strain, then the free energy will also decrease quadratically as a function of applied strain, and that looks like a jump in the elastic modulus. That is a jump in the elastic modulus. Now we can consider two strains. So one is an orthorhombic strain along the 1, 0, 0 direction, and another one has 1, 1 principal axes. Under the tetragonal symmetry of strontium ruthenate, the slope dTc by d strain must be 0 for both of these strains at 0 strain. Therefore, a jump in the elastic modulus is not possible, but one is observed. So this is the elastic modulus C66 that corresponds to this shear strain, and there's a jump of about 10 parts per million, actually about 20 parts per million at Tc. So this symmetrically, this is only possible when we have a two-component order parameter. It is only possible when we have these linear dependencies on Tc that of Tc on strain that extrapolate to 0 stress. So now the question, I'll spend about 5 more minutes trying to explain how we can reconcile, considering whether we can reconcile chiral order, in particular xz plus minus yz, with the data that we have seen. So the central conundrum is this. The zero stress limit of the slopes dTc by d stress and dt TRSB by stress are inverse to the heat capacity jumps at these transitions. You can get that straightforwardly from Ginzburg-Landau theory. That is a constraint which follows from these components being degenerate on the tetragonal lattice. So therefore, our heat capacity data say that dt TRSB by distress should be at least 20 times dTc by distress. If you remember in the heat capacity data, the heat capacity anomaly here was at most 5% that at Tc. So under hypothesis of xz plus Iyz superconductivity, what this means is that the superconductivity would be very nearly nematic. So if there's a very weak heat capacity anomaly at TRSB, then that says that dxz order would have nearly as much condensation energy as xz plus Iyz. But coming back to our data, the central conundrum is this: what we see is the opposite. We see a TRSB a time reversal symmetry breaking temperature that does not change very much, but a TC that increases rapidly. So our proposal for the way to reconcile this with data is through inhomogeneity. All real samples have a degree of internal inhomogeneity. They all have long length scale disorder. This is because all of the samples have some density of ruthenium inclusions that's intrinsic to the growth process. So when we have some internal strain disorder, then that is predicted to round off the, that will round off the cusps that are predicted in the clean limit. And we propose that this is the reason that no cusps were seen in the scanning SQUID experiment. As we go to high stresses now, we have this very strong quadratic increase in TC associated with the approach to the Lifshitz transition. So the approach to the Lifshitz transition is a very strong nonlinear change in the electronic structure of strontium ruthenate, and therefore we argue that at high stresses, linear extrapolations from the zero stress behavior do not apply. We are no longer in the low stress limit. And one further thing I'll point out is that a hypothesis of XZ plus or minus IYZ could explain thermal conductivity data. So strontium ruthenate shows what is known as universal thermal conductivity. That is a thermal conductivity that is independent of residual resistivity. This is usually an indication of symmetry-imposed line nodes, and for X plus IYZ, that could be this line node here. For vertical line nodes, it's actually challenging to get the right angle of opening. Because strontium ruthenate has a very long mean free path, it's very clean metal, one tends to get complicated gap structures in the plane. And so getting this angle of opening that would give you universal thermal conductivity is quite hard. But if we had interplane pairing, then we can imagine interlayer correlations, and that gives us this angle, this correct angle opening. We really don't expect correlations extending over a larger, we don't expect correlations skipping layers, which is what you would need in order to get a complicated structure in KZ. Another recent proposal is that interorbital pairing could give us XZ plus or minus IYZ order. So interorbital pairing becomes possible when the Hund coupling is strong. The Hund coupling is what drives this pairing, and spin-orbit coupling is also strong. And these are both true in strontium ruthenate. How strong these things need to be is a matter of ongoing debate. So this interorbital pairing has been proposed for a couple of materials, but in most materials it would be indistinguishable from conventional pairing. The possibility that it offers is that this structure, this XZ plus IYZ structure, could be encoded within the orbital structure of the Cooper pair, and not the case. And we therefore do not need strong interlayer correlations in order to get such a structure. And what's potentially exciting about strontium ruthenate is that interorbital pairing might be the only way to get such an order. And then there have also been recent proposals for S plus ID and D plus IG, and I point out the references to here. Out of time, so I'll stop here, and thank you for your attention.